let's have a little look at chemical equations. These are the equations that go along with chemical reactions. Right, so let's have a look at one. Here's the starting of one. Let's say you took some magnesium ribbon and you held it with metal tongs, not with your fingers, and you placed that magnesium ribbon into a Bunsen burner. That would actually react the magnesium with the oxygen, okay, not with the fire from the Bunsen. Nothing actually reacts with fire. That's just energy. You don't react with the energy. What the magnesium is actually reacting with is the oxygen in the air, and you get to make some of this stuff. Let's take a look. I'm good.
Yeah, me too. Go.
Go?
Yeah. Oh, it sounds cool as I thought it'd be.
That's cool. That was cool.
Okay, so we can see that magnesium burns with this nice bright white flame, right? Really, really bright. So that's the reaction we've seen, and here's the reaction equation, the chemical equation. Now, what do all the different parts mean? Well, you see we have an arrow, and on the left of the arrow, in this case the magnesium and the oxygen, these are called the reactants. These are the things that react together. And on the right of the arrow, we have the products, the things that are produced. Now, in this case, we actually only had one product, right? That magnesium oxide. But that's fine. We can have one product, two products, three products, etc. But on the left of the arrow, reactants. On the right of the arrow, products. Now, this plus symbol, we can sort of read that as saying reacts with... Okay, so magnesium reacts with oxygen, and then this arrow we can read that as to form. So what we have with this reaction equation is that magnesium reacts with oxygen to form magnesium oxide. Okay, so let's just get rid of those, make it easier to see. There we go. So magnesium reacts with oxygen, just oxygen in the air, and we get that magnesium oxide, that nice white powder. Right. So one thing we actually could note about now is that the product formed actually had very different physical properties to the things that made it up, right? So if we're just looking at the magnesium ribbon first off, magnesium ribbon, describe it. Well, it's a shiny silver metal. The oxygen, let's describe that. Well, that's a colorless, odorless gas, right? You couldn't see it, couldn't smell it, it's a gas. And then we form this magnesium oxide, this white powder. So products often have very different physical properties than the elements that went into making up those compounds. Cool, great. So we're not going to talk about compounds too much. We're looking at chemical equations. Okay, now let's just tidy this up a bit and we'll talk about this equation that we had. Let's just get rid of all the scribbles. Okay, back to here. Now, this equation is actually not quite finished. What about the heat? Well, we just don't need to show it. Simple as that. If you really, really want to show the heat, you could put it here. So now this, written above the arrow, this says that magnesium reacts with oxygen in the presence of heat to form magnesium oxide. Okay. With senior chemistry, when you're doing thermochemistry, you will actually put heat into equations when you're looking at enthalpy and energy there. Sometimes the plus heat will be on the left, sometimes the plus heat will be on the right, but that's senior thermochemistry. We're not looking at that right now. So for now, if you just, if you really want to say, I had to heat it, write the word heat above the arrow there. Cool. Oh, actually, we should talk about that arrow because some students like to do this. Okay, because when we take the magnesium and the oxygen, we get this magnesium oxide. That is so wrong. Please don't ever use an equal sign when you're writing a chemical equation. Equals, what does that mean? Is the same as, well, guess what? Magnesium and oxygen gas are not the same as magnesium oxide. They're not. They're very different. We've already talked about that. Magnesium oxide is a white powder. Magnesium is a shiny silver metal. Oxygen is a colorless, odorless gas. What we have on the left is not anything like what we have on the right. Don't use an equal sign. Definitely go with that arrow. So this equation, it's still actually not correct. What we need to do is balance the equation, okay? In a chemical reaction, there's no matter created or destroyed. You cannot create or destroy matter when you're doing chemistry. So we need to have a balanced equation. What this means is anything that's on the left has to be here somewhere on the right. So on the left we started with a magnesium and we finished with a magnesium. The magnesium is fine. We started with 2 oxygens on the left of the equation. How many oxygens do we have on the right of the equation? Only 1. Well, that says somehow we've managed to delete an oxygen. It's just floating around in the universe somewhere. No, we can't do that. We can't just delete an oxygen. Oh, well, let's put it in here. Let's make the equation say MgO2. Now we've used our magnesium and we've used both oxygens. So yes, now it's good, except it's not. That's not the formula for magnesium oxide. The formula was correct as we had it, MgO. That's the correct formula for magnesium oxide. So we can't just add another oxygen into there. What can we do? Well, we need to use our 2 oxygens because we can't just delete some matter. But every magnesium oxide we have only uses 1 oxygen. Well, why don't we just make another magnesium oxide? What if we actually had another magnesium oxide? Okay, now we would be using 2 oxygens, 1 for each molecule, right? Great, that would be the oxygen happy. Well, hang on, now we've used 2 magnesiums, and we only started with 1. That's okay, we can just put a 2 in front of the magnesium to say actually we had 2 of these things, all right? And let's do that with the magnesium oxide. Instead of writing MgO plus another MgO, let's just, actually, if we give ourselves more room, there we go, let's just put a 2 in front. Okay, and now's a good time to talk about what the numbers actually mean. There are 2 sorts of numbers we can put in our chemical equations. We can have these big numbers at the front of the thing, whatever it is, the molecule or whatever you're talking about. We've actually got a number here in front of that one too, but it's like algebra. The number is a 1. Okay, so just like algebra, if it's a 1, we tend to just not write it. Cool, so we can have numbers in front. What that number says is how many of this thing do you have? So I have 2 magnesium atoms, or later on you'll talk about moles of magnesium. The SI unit for the amount of a substance is the mole. I made another video about that. Watch it at your leisure. But for senior chemistry, when you're at college, you'll talk about moles. So 2 moles of magnesium reacts with 1 mole of oxygen to give 2 moles of magnesium oxide. For now, you can just think of it as 2 of these things. All right, so in this case, 2 magnesium atoms will react with 1 oxygen molecule, right? 2 oxygen atoms, but there's 1 molecule there. And that will give us 2 molecules of magnesium oxide, okay? So that's fine. That's one of the numbers. That's the big number in front of the thing you're talking about. Now, here is a little number, subscript, okay? It's not a number in front, it's subscript. It's written lower down, and it's usually written a bit smaller than. Now that says how many of the atoms do you have in that stuff that you're talking about, right? Let's do a clearer example. Let's talk about H2SO4. H2SO4, hopefully you'll know of as sulfuric acid. Okay, if I want to make one of these particles, if I want 1 molecule of sulfuric acid, what do I need to actually make it? Well, I'm going to need 2 hydrogens. Okay, because this subscript number says I actually need this many of that type of atom. Okay, sulfur doesn't have a number down there, but remember, it kind of does. It's a 1, right? It's algebra, we don't write the 1s, yeah? So I'm going to need 2 hydrogens, I'm going to need 1 sulfur, and I'm going to need 4 oxygens. Okay, if I have 2 hydrogens, 1 sulfur, and 4 oxygens, if I put them together just the right way, I can actually make 1 of these molecules of sulfuric acid, 1 dihydrogen sulfate. All right, so that's what the numbers mean. So a big number in front is how many of that molecule you have, and the little numbers within the molecule, the little subscript ones, how many of that type of atom, that the number is just behind, how many of that type of atom you need. All right, so if I had, let's say, 3 molecules of H2SO4, how many hydrogens will I need? Well, I'd actually need 6 altogether, and 3 sulfurs, right, and 12 oxygens, because every molecule I need 2 hydrogens, 1 sulfur, and 4 oxygens. But if I had 3 of those molecules, well, I'm going to have to multiply these numbers by 3, right? Because those numbers are per molecule. If I had 3 molecules, I'm going to need 3 times as many. Okay, so hopefully you're getting right with those numbers. Let's look at some more examples. Okay, so let's take another reaction. What shall we do? Let's take our iron and rust it. Okay, so we left our bike out in the rain. Bit unfortunate, there's a lot of rain going on at the moment. Hopefully your bike isn't out in the rain, but if it is, this may happen. This is not going to happen overnight, but eventually. It takes time for things to rust. So rust is essentially iron reacting with oxygen and forming this thing called iron oxide. Okay. Now, the thing is, we said oxygen before comes in twos. Okay, oxygen is a diatomic molecule, right? Diatomic, 2 atoms. Right? Lots of these little gases are diatomic, like hydrogen gas. We have chlorine gas, fluorine gas. These are things like we've got N2, Cl2, I2, O2 in this case. So they're often diatomic. Now, we need to balance this, okay? Because we can't create or destroy matter in a chemical reaction, right? The thing is, with this one, the formula is actually going to be Fe2O3. Where the heck did those numbers come from? Well, let's have a quick look. Actually, do you know what? Just before we do this one, let's go back to that magnesium reacting with the oxygen in the air to give us our magnesium oxide. Now, we talked about, MgO is the correct chemical formula for magnesium oxide, but how do we know that? How do we know that that formula is correct for magnesium oxide? Well, there are a couple of ways. There's the long way, and then there's the much, much quicker, shorter way. Here's the long way. Let's look at the long way first. So we look at magnesium and we think to ourselves, right, what is magnesium going to do when it reacts with the oxygen? Okay, we need to look at the electron arrangement. Now, magnesium is number 12 on the periodic table. That says it has 12 protons. It will also have 12 electrons. So let's write down the electron arrangement of magnesium. There it is. We can do the same thing for oxygen. Oxygen is number 8. It will have 8 protons. It will also have 8 electrons. We write the electron configuration, and there it is. Now, atoms react in order to get 8 valence electrons. Okay, so how can these two things get 8 valence electrons? Well, magnesium, it could pick up 6 more, or it could get rid of those last 2. What it does is get rid of those final 2. Gives them the boot. It's easier to work with 2 electrons than 6, right? So magnesium gets rid of those 2 electrons. Oxygen grabs them. Those 2 electrons floating out in the universe, oxygen says, hey, sweet, I'll take you. And this then gives both of the atoms an electron configuration with 8 valence electrons, right? 8 outer shell electrons, because those 2 aren't there anymore. And they have been picked up by the oxygen, so instead of 6 at the end, oxygen will have 8 at the end. Okay, so this is the electron arrangement of the atoms once they've reacted. They both have 8 outer shell electrons, or we say 8 valence electrons. Now this makes them more stable. Atoms react to get their 8 valence electrons because that stabilizes them more. Okay, so they're more stable. Great. So what actually happened when magnesium kicked off those 2 electrons? Well, electrons have a negative charge. So if you're getting rid of an electron, what's left behind is positive. Magnesium actually kicked out 2 electrons, so what's left behind is 2 plus. Oxygen, on the other hand, picked up those 2 electrons, so now it becomes 2 minus. It has an extra 2 negative charges, right? Remember, before atoms react, they have the same number of protons as electrons, so same number of pluses as minuses, and all those charges cancel out. Great, atoms are neutral. Okay. Well, guess what? Compounds are also neutral. So the compound here, MgO, we know is correct, because if we just took one of this magnesium with its 2 plus charge and one of this oxygen with its 2 minus charge, if we put those together, all of those charges will cancel out. All right. So if we write it up here, the O2 minus, this 2 plus cancels out that 2 minus. We don't have any charges left over, and that works out nicely because compounds don't have charges, and there's our formula for magnesium oxide. Okay. If it were MgO2, right, like that, we would actually have 2 minus charges left over. Can't do that because compounds don't have a charge. So we know that that is actually not the formula. Magnesium oxide is actually MgO. Now, if we go back to the example that I started doing before, the iron rusting out in the rain. Iron oxide is rust, and that's this Fe2O3. Right, how do we get that Fe2O3? Well, here's the thing. When iron reacts, in this case, it's going to lose 3 electrons. And if it's losing 3 electrons, what's left behind is going to be 3 plus. Oxygen, we know, gains 2 electrons, right? We just saw that before. So oxygen wants to become O2 minus, right? This is the oxide ion. These are ions. An ion is something with a charge. I've got another video about ions. You can watch that at your leisure as well. Okay, so an ion is either an atom or a group of atoms with an electric charge because they've either lost or gained electrons. So iron loses 3 electrons, so it becomes 3 plus. And the oxygen gains 2 electrons, so it becomes O2 minus, the oxide ion. And if you watch my other video, you'll know that the negative ions finish with IDE. So we call it the iron ion. I know those words kind of sound the same, right? But it's the iron ion, or we talk about the oxide. We don't talk about the oxygen ion, we talk about the oxide ion. The negative ions finish with IDE, right? For the monatomic ones, if it's made of just the one atom, one type of atom. Great, let's just get rid of that. We don't need that hanging around. Erase, gone. Now, if we just put these things together, if we just put one of each of these ions together, we would still have some charge because these 2 minuses would only cancel out 2 of the positives. We would be left with FeO plus. It would still have a positive charge. Remember, we can't do that because compounds don't have charges. All charges must cancel out, okay? So if we did that, we would have too much positive charge. So let's just use another one of these guys. Okay, and we can cancel out more of the positive charge. Yes, except now we've got too much negative charge. So we have to add some more positive. So let's use another positive. And now we've got too much positive. Let's use some more negative. Oh my goodness, could keep going forever. Except, wait, actually, now it's going to work out. Because now we have in total 6 minus charges and we have in total 6 positive charges. If we put all of these 5 things together, all of the charges will cancel. Okay, our 6 negatives will cancel out our 6 positives and our compound will not have a charge, which is good. Look, right here, there's no charge because it's a compound, they don't have charges. Now, what did we actually use? We used, well, here's one iron ion, here's another iron ion. How many did we use? We used 2 of them. So we actually needed to use 2 of these atoms. How many oxides do we have? We got 1, 2, 3, and sure enough, look, we needed to use 3 of these oxygen atoms. Okay, so that's what those numbers mean. Now that was the long way to do it. There is, in my mind, a much quicker and simpler way to come out at the right formula, right? The right chemical formula for the thing that you're talking about. Let's just get rid of this and we will jump to a periodic table. Well, the top of a periodic table anyway. Here's one. Here's the top of a periodic table. IUPAC, that's the International Union of Pure and Applied Chemistry. They basically give us all sorts of guidelines on how to do chemistry. Right, so hopefully you've done this with your periodic table. And if not, I suggest you do this with your periodic table. Above group 1, what you should have is a +1. Above group 2, you should have a +2. Above group 13, you should have a +3. Okay. Now, let's start from the other end. Let's ignore group 18. Above group 17, you should have a -1. Above group 16, put in a -2. And above group 15, a -3. Okay, nothing above group 14. Now, why do we put these in? These are the charges that the things form. Remember magnesium, it formed 2+, didn't it? Look, it's in group 2, it forms a 2+ charge. Okay. Oxygen, well, that's in group 16. And remember what it formed? It formed a -2 charge. Well, that should be an arrow. There we go. Okay. Sulfur. What's the ion of sulfur? The sulfide? Well, it's going to be S2-. Now, I could look at the electron arrangement of sulfur. I could say to myself, okay, it's number 16, it's got 16 protons, it will have 16 electrons. Let's write the electron arrangement, it's going to be 2, 8, 6. What will it do? It will somehow pick up 2 more electrons to make it 8. Yes, great, there's the octet rule satisfied, it'll be stable, it got 2 electrons, that's picking up 2 minus charges. Oh yeah, it's going to be S2-. Or, I could do it like I did just before, I can say, well look, it's in group 16, it forms a -2. Anything in group 16 is going to have a 2- charge on it. right, when it reacts and forms an ion. So that's why these numbers above your periodic table, oops, just got rid of one there, +2. That's why these are so helpful, because they're a shortcut. Okay, I showed you the long way. You can work out what charge these ions will have, but this is the shortcut. Okay, now you'll notice iron is way down here, and I didn't write the +3 above this one, did I? No. This general rule is good for the groups that I've mentioned, right? So it's good for group 1, group 2, group 13, group 15, 16, and 17. Okay, couple of things. Firstly, we didn't put anything above group 18, right? Why not? The noble gases, they tend to not react, don't they? Why not? They've already got 8 valence electrons. That's why things react. Okay, so if these have already got 8, they're not going to react. Now, group 14. Well, that's in the middle. Is it going to be a +4? Wait, it could be a -4. Which is it going to be? +4, -4. It's actually not. It's not going to gain or lose electrons. It's going to share them. It's going to form a different type of bond, a covalent bond, instead of an ionic bond. Covalent bonds you will absolutely cover in college chemistry in year 11. You'll talk all sorts of different bonding types, but in high school you will not. In high school it's generally kept to ionic bonding. So now that iron, well, yeah, we left out these transition elements. Oh, I'm still on the highlighter, goodness me. We left out these transition elements, right? These 10 columns. The thing about transition metals is that they can form different ions. Like iron could actually form the 2+ or the 3+. It could lose 2 electrons, or it could actually lose 3 electrons. Copper, we talk about the copper ion. Well, are we talking about Cu2+? Yeah, most of the time, but sometimes actually just Cu+. Transition metals get a bit messy. They can lose different numbers of electrons. Now, if we jump back to the example I gave before, how did you know that the iron would form the Fe2+ or the Fe3+? Yeah, in this case, actually, maybe not the best example. You're just going to have to trust me. Okay, in this, it's going to form the Fe3+. It depends what it's reacting with and the conditions of the reaction, but take my word for it, we're forming a 3+ here, okay, for this one. And for my next example, I'll use a better example. Right, so that's hooking up with some oxide, right? Now, if we put these together, we're not going to be cancelling all charges, right? We'd need another oxygen to give more negative, then another ion to get more positive, then another oxide ion to get more negatives. And eventually it'll work out once we had 6 pluses and 6 minuses. There's a much quicker way. If the size of the charge is different, so okay, we're talking the size of the charge here. The size is a 3 and this size is a 2. Okay, if the size of the charge is different, drop and swap. All right, this is a good old method. We drop and we swap. So you'll note the charges are written up high, superscript, drop them down to become subscript. That 3 drops down and it's down here. But then also swap. So it's no longer with the iron, it's over here with the oxygen atom. All right, so the 3 comes down there. So we're going to be left with an Fe, and there's going to be a 3 down here. And then we do the same thing with the 2. The 2 is going to drop down. It's going to swap to the other thing, the other chemical species. And what we're talking is the iron. So there'll be a 2 here. And voila, there's the formula, which we actually had in the equation already. Okay, so this is the drop and swap method. We can do that if the size of the charge is different. If the size of the charge is the same, you just slap them together. Now we've already seen this with our Mg2+, and we hooked that up with some O2-. What did we get out of it? We just slapped them together for our MgO. Okay, and when we're doing these, forming these ionic compounds, that's when this really comes into its own, right? These little numbers here. Okay, so let's go back to this one. A couple more examples. Let's make some, I don't know, aluminium fluoride, right? Let's take some aluminium and let's react it with fluorine. So aluminium is a metal, fluorine is a gas, it's a diatomic gas, so there it is, and we're going to make some aluminium fluoride. What the heck is the formula for aluminium fluoride? Well, that's where we jump back to the periodic table and we see that aluminium is in group 13, and anything in group 13 is going to be a +3 charge. Now fluorine is in group 17, and anything in group 17 is going to have a 1- charge. right? So now, knowing that, we can jump back here. We know that we're going to be putting our Al3 plus, because it was in group 13, forms a 3 plus. We're going to be hooking that up with our F minus, our 1 minus, and the size of the charge is different. We're going to drop, we're going to swap. Okay, and we're going to come out with AlF3. That is the formula for aluminium fluoride. Okay, just by using this drop and swap method, it's much quicker, right? So we could have written out the electron arrangement for both aluminium and fluorine, and worked out, well, what will the atom need to do to get those 8 valence electrons? Blah blah blah. It's long-winded, takes a bit of time. Like it's not a hassle. But I think this drop and swap method is just so much quicker. Some more examples. Let's make calcium nitride. Let's take some calcium metal and we react that with nitrogen. Nitrogen, guess what? It's diatomic, right? I told you lots of these little gas molecules, they are diatomic. And this is going to make, well, what is this going to make? Calcium is in group 2. It's going to form a 2 plus charge. So we can just write this down, calcium 2 plus. Nitrogen is in group 15. It's going to form a -3 charge for the nitride ion. Okay, is the size of the charge the same? No, they're different. That's great. We've got something to do when the size of the charge is different. We're going to drop and swap. So the 2 is going to drop and go over to the nitrogen. The 3 is going to drop and come over towards the calcium. We're going to end up with Ca2. Okay, it's dropped, so it's subscript. And then N, oh, wait, hold up, that should be a 3. We're going to end up with Ca3 N2. There we go, that's better. So that is the formula for calcium nitride. Okay, nitride, because remember the negative ions, they finish with IDE, right? Now, when we're writing these formula, we always put the positive one first. So it's never nitride calcium, it's always calcium nitride. Okay, so there we go. We've had a little look at chemical reactions. So we say that calcium and nitrogen, in this case they are the reactants, and they're forming this product of calcium nitride. We know how to get the formula for what they're forming. Now, we're actually not finished though, are we? Because we have to balance our equations, right? There's always that final step of balancing your equations. So this says I started with 1 calcium and I finished with 3. Well, that's not right because we can't create matter. So if I want to finish with 3, start with 3. The big number in front tells you how many of those things you have. Well, let's just start with 3 calciums, no problem. What about nitrogen? Well, I need to finish with 2 nitrogens. Hey, that's okay because I started with 2 nitrogens. So that is balanced. Now, I didn't actually balance this on back here. Aluminium and fluorine. I start with 1 aluminium, I finish with 1 aluminium. Aluminium is balanced. Grand. I start with 2 fluorine atoms. I finish somehow with 3 fluorine atoms. Nope, not happy with that. Can't create matter, right? So what do we actually need to do? We need to balance. So in this case, I need more fluorine at the start. I need to have more fluorine here. Okay, so let's say I had 2 there, but now that's too many because that gives me 4, right? Because every molecule, there are 2 fluorine atoms, but I've got 2 molecules. So in total, I've got 4 fluorine atoms. And at the end, I've only got 3. Well, we can use more fluorine atoms. Let's just have another molecule of that. But that now says I need to use 6 fluorine atoms. Well, that's fine. We can get 6 fluorine atoms. Let's take out this 2. Let's get rid of that and just make it a 3. And now I have used my 6 fluorine atoms at the start. I've got my 6 fluorine atoms at the end. Fluorine is now balanced. Now you'll see in balancing that, I'm sort of going back and forth. All right, so this wasn't, then I had to go more on the left, more on the right, more on the left. You keep going back and forth until it all works out. The aluminium was actually balanced at the start, but now it's not. Okay, because now I'm suddenly using 2 of the aluminium atoms, right? 1 per molecule, but I have 2 of those molecules. So I'm actually going to need 2 aluminium. So that's fine because being a metal, we can just write it with the symbol, but I needed 2 of them, no problem. Okay, no problem at all. So we always have to balance our chemical equations. Let's just do a couple more. Say we took some metal. What's a good metal? Aluminium? Sure, we'll take some aluminium. Let's dissolve it in our sulfuric acid. So, okay, let's take some magnesium, no, not magnesium, some aluminium, and we'll put it into H2SO4, that's sulfuric acid. What are we going to get? Well, we're going to get a couple of things. In this case, we're going to get 2 products. because when you take a metal, put it into acid, you get hydrogen gas given off. You also get a salt. Now, a salt in chemistry just means an ionic compound, right? So we're going to get hydrogen gas straight up, okay? Because you take metal into acid, you get hydrogen gas produced. So that's fine. We're also going to get a salt, and our salt is going to be aluminium sulfate. Now that's going to be a 2, and the sulfate is going to be a 3. We'll get to this in a sec, right? Hydrogen, we can see, is diatomic, right? Those little gases, they tend to be diatomic. Now, we're hooking up our aluminium with our sulfate. Aluminium, we know, is 3+. Okay, sulfate, this is an ion because it's a group of atoms with a charge. Remember, an ion is either an atom with a charge or a group of atoms with a charge. In this case, it's a group of atoms with a charge, and the charge is 2-. And so 2- is the sulfate ion. Now, the size of the charge is different. That's a 3, that's a 2. We know what to do. We're going to drop and swap. Okay, so the 2 comes down and across to the aluminium. There it is, right? Now that 3 is also going to drop and swap. It's going to be here. The trouble is with this, it looks like SO43. Well, actually, we don't want to use 43 oxygens, right? We need to say, instead of, 1 S and 43 oxygens, we need to say 3 sulfates, right? So we're going to treat this thing as an entity, this ion. So this thing, we treat it as one thing, and we need to say 3 of those, okay? But in chemistry, we tend to not draw big circles around things. We group things together, just like you do in maths. We use brackets. And then that 3 we could probably write up a bit closer there. Well, that was a messy one. Right at the edge of my screen, so, oh, well, that'll do. So there we go. We've used brackets to group the ion, okay? The drop and swap method still works exactly the same. It's just that we use brackets to group the polyatomic ions. So there you go. That was, well, I'd like to say a brief look at chemical equations, but I think I talked too long. Anyway, so that wasn't a brief, but it was a look at chemical equations.
Don't forget to hit the like button. Yeah. And subscribe to It's Up Here. And here's another video.